the integral test. So we consider the following situation. So we assume we have a series, and we have for a series that all the terms are positive, and the terms are decreasing. Also, let's assume that we have function f of x, and assume that we have function f of x such that f of n equals to a of n when n greater or equal than 1. Okay, so let's have a look at the picture. Actually, we're going to look at the two pictures, but so let's have a look at the graph of function f of x. So function is positive and it's decreasing. So let's function y equals f of x. Notice that if you mark 1, 2, 3, and 4, and so on, and value function at 1 is a1, that's what we agreed on. Value function at 2 is a2. Value function at 3 is f of 3. The value function at 3 is a3. The value function at 4 is a4, and so on and so on. So if that is a1, and if I draw a rectangle of base 1, then area of this piece is going to be a1. If I draw a rectangle of base 1, that height is a2, base is 1, so area of that rectangle a2. If I keep on going, I get a3 and so on, a4 and so on. So what you notice from here is that integral 1 to infinity f of x dx is going to be, it's going to be less or equal. It's going to be less or equal than a series, value of series, and from 1 to infinity. That's the first picture I want to refer. Look on a similar picture. So again, mark 1, 2, 3, 4, and so on. Then instead, now let's look at this picture one more time. Now, instead of building rectangles the way we did, we'll do them slightly differently. So we'll look at our height at 2, which is f of 2, which is a2, and we build rectangle, and that's going to be a2, then a3, then a4, and so on. So what you notice is that now if we add up all those rectangles, which is going to be n starting from 2 to infinity, that is going to be under the area under the curve. That's going to be less or equal than integral from 1 to infinity f of x dx. That's two pictures we want to see. Now, let's see what implies. If we have integral from 1 to infinity f of x dx equals to plus infinity, and from here it follows, using the first inequality right here, we conclude that series an from 1 to infinity is going to be greater or equal to plus infinity. So we conclude that our series will be equal to plus infinity. Okay. So if integral equals to plus infinity, then the series equals to plus infinity. Now let's look at another possibility. What is happening? Here we have convergent integral. Convergent means equals to finite number. Okay, now we're going to look at the second inequality which we got. So from here, we're going to get sum n from 2 to infinity an is going to be less or equal than integral from 1 to infinity f of x dx, which is equals to finite number. So we conclude from here that n from 2 to infinity an cannot be equal to plus infinity. And because we're going to add up positive terms, then we have only two possibilities for positive term series. For positive term series, we have only two possibilities. Either we keep on adding numbers and we're going to get infinity, or we keep on adding the numbers and it's going to be equal to finite. There is no oscillation up and down for positive term series. So let's have a look one more time what you got. If integral is convergent, then corresponding series is not equal to infinity. Because it's positive term series, we conclude that the series is convergent. Okay. So if I now put these two pieces of information together, that piece of information and this piece of information together, I'm going to be able to write down so-called the integral test. So let me summarize it and write it down and maybe manipulate it more formal way. So the integral test. So essentially that's the statement which you already did. Suppose we have series, it's a positive term series. And also suppose f of x is, and f of x is decreasing and continuous. For x greater or equal to 1. Also suppose f of n equals to an, when n greater or equal than 1 integer. Then conclusion is, if you look at the series, and if we look at the improper integral from 1 to infinity f of x dx, we were both convergent or both divergent. So series and the integral will do the same. They either both converge or both diverge. That's what the statement of the integral test. So let me try to illustrate it on an example or two. Let's look at the so-called harmonic series. Let's have a look at so-called harmonic series. Okay, so we want to know if it's convergent or divergent. Okay, so let's try. So we're going to look at a function f of x which equals to 1 over x. F of x is going to be decreasing. And f of n is going to be equal to 1 over n. So we are satisfied the conditions of our integral test, so we are allowed to use the integral test. So we conclude that they're harmonic series 1 over n and from 1 to infinity, and the improper integral 1 to infinity 1 over x dx will do the same. By do the same, I mean they both converge or both diverge. Okay, so instead of working with the series 1 over n, I'm going to pay attention to that integral 1 over x dx on improper integral from 1 to infinity, and I will make a call. So integral 1 to infinity 1 over x dx, easy to find antiderivative ln of x 1 to infinity, so we're going to get ln of infinity minus ln of 1. Ln of 1 is 0, ln of infinity, infinity, so we have and infinity. So integral 1 to infinity 1 over x dx is divergent, equals to infinity. And so is, if you like, by the integral test, so is the series 1 over n and from 1 to infinity. So series 1 over n is divergent. So that's approximately how we're going to be using the integral test. Let's do one more example. Here we have series, and from 2 to infinity, 1 divided by n ln of n. And we want to know whenever the series converges or divergent. So let's try. So we start with 1 over n ln of n. So from here we can easily see the function we want to work with, 1 over x ln x. And we want to give this function on x greater or equal than 2. So f of x is decreasing because the denominator is increasing and numerator same. Denominator is increased, numerator stays the same, so the fraction is decreasing. Okay, and that is when x greater or equal than 2. Okay, so we're going to apply the integral test. Now we're allowed to use the integral test. So we get approval to apply the integral test. So we get approval, so we're allowed to start working on it. Because we checked that our function is decreasing, and also mentally I also checked that my series has positive terms, because we have 1 over n ln of n, and from 2 to infinity, when n is bigger or equal than 2, when n is positive, ln of n is positive, product of positive, so I kind of mentally did that. So we're allowed to do the integral test. So let's try to do it. So from series, we switch to corresponding indefinite integral, and it's going to be from 2 to infinity. So we're going to do substitution u equals ln of x. Notice that du equals 1 over x dx. So you notice that 1 over x dx is what du right here. So we're going to get 1 over u du. So we're going to get ln of u x from 2 to infinity. Doing back substitution, so we're going to get ln of x from 2 to infinity. Substituting infinity, we're going to get ln of infinity. We're going to get ln of infinity minus ln of 2. Ln of infinity is infinity, so we're going to get ln of infinity minus ln of 2. ln of infinity is infinity, so we're going to get infinity minus ln of 2. So at the end we have infinity. So we conclude the integral from 2 to infinity 1 over x ln x dx is divergent. Therefore, by the integral test, corresponding series n from 2 to infinity 1 over n is divergent